Okay, so a couple of important things. Test 1 was Tuesday. Of course, Tuesday was the crazy day, so we had lots of people who missed the test and need to do makeups tomorrow. So once they do the makeups, once I'm complete tomorrow doing makeups, which it seems is going to take up my whole day just about tomorrow, but that's okay. To review your exam, your results afterwards, you have to have the lockdown browser, right? So this is information about that, where it is on campus, how important it is to review your test as soon as possible. Remember to look at the objectives that each question is related to, because that's your study guide, right? Everyone wants a final exam study guide. You already have it. I let you guys see your tests, right? From what you got right and what you got wrong, you write your own personal study guide as to what objectives you need to review, right? And once I open the test, it's going to be available all the way until the final exam, right? So once everyone's taken the test, you'll be able to see your individual results. You just have to open it in the lockdown browser, right? So you can download that for free. The link is in this on this page here for you guys, as well as detailed information. So, and once everyone gets done too and I make it available, I'll post an announcement for you guys so you know that it's available. So the next thing, we're still working on the chemicals to clean page, and so my last ditch attempt, right, on the day of the exam, there's the even video on how to do the assignment when you click on it for modules, and this is the actual page. We're on the second table. In this box right here, it says activity level, right? So something like one of the activity levels from table 1. Is it a strilliant, high level? Is it intermediate? Is it low level? And then you explain that in the section next to it. So for this one, the person needs to put, right? And actually, they have it here. You just need to write it over here, right? Otherwise, you won't get your points. And get that done like yesterday, right? So there's a couple, and I actually already even graded these. If you look at your grade, it says incomplete right now, and it tells you need to fill in this box. So you need to finish that up. So it looks like just a few people are still working, but it was due before, right? So get it done, because once I grade one more time, I'm not grading again. You won't get your points. Okay? Any questions on that? All right, so moving on to this next unit, or module they call them in Canvas, so I got to get used to calling it a module instead of a unit. The first assignment I wanted you to do is read these web pages. And so these are really good overviews, and in fact, I'll go to my student view right now. So it'll look like it does for you guys. So there were two really short web pages, right, that I wanted you to do, right? Notice I already turned it in, but you could resubmit if you needed to. But for some of you guys, the text box doesn't automatically pop up. I guess it depends on which browser you're using. I don't know. But you have to click here. It would say submit assignment for you if you hadn't done it yet. Once you do it, you'll see that it'll say you've turned it in, when you turned it in. You can click on the details and see what you wrote. Of course, I wrote a bunch of gibberish because I was just trying it out. And then under grades too, you'll know if you turned it in because you'll see a T there, right, that you did a text entry. You have to write 2 comments, 2 things that you like about the web pages, so I know you read them, right, because I have no other way of knowing. It's the easiest 10-point assignment on earth, y'all. You can play the game if you want, right? You can comment about the game if you want. But more importantly, those 2 web pages I want you to read. It's a really good overview of the immune system, which is our whole next module. All right, so those of you guys that have already done that are shaking your heads. Yeah, wow, that was actually worth my time, right? Okay, so get that done, because same thing. Even though the deadline was today, I haven't graded them all yet. So get it done before I grade it, and I might actually grade it, and you won't lose points. So that brings us to today's lecture. So under our objectives in PowerPoint, right, I have today's lecture. And we're going to go to that right now. And I had even posted a nice big long announcement to you guys, telling you all of that. So we're going to start out with the innate immune system. We're going to define that and look at that next time. And as I warned some of you guys, if you were paying attention before the test, that I was going to jump to the end of the chapter, right? And the reason for that is inflammation is paramount to immune response, right? So I find if that's the first thing I talk to you guys about in immunology, when I keep saying what is the most common immunological response, you will say inflammation, because I covered it first, right? So we're going to even watch some cool videos today. Hopefully I can get my audio up. And I've worked extensively on this lecture, so hopefully you guys read ahead and we get a good, strong foundation for this module. So for inflammation, I want you to be able to outline the inflammatory process, right? So the major steps. Focusing really in on how this process initiates. How does it start? And then what are the outcomes, right? What happens once this starts? What are, you could say, the benefits of it? So what's the purpose? Anyone want to share one of their purposes they wrote down? Nobody this morning? Are still asleep? Just off the cuff, what do you think? When someone says inflammation, it's to attack microbes, right? So we want to attack any invaders that may have gotten in to the body. Anything else? What do you experience? Notice it says down here the 4 cardinal signs. What do you see or feel when you know you have inflammation? Redness, swelling, not so much itching. Itching could be something else, but can happen with some inflammatory responses. Heat, pain, definitely pain, and sometimes loss of function. So, but why does it get red, right? Why does it swell up? Why do you experience this pain? Well, it has to do with what's happening in this process, right? So, but why is it happening? It's happening, its purpose is to contain the site of damage, right? You'll notice that inflammation, for the most part, especially when you have a cut on your finger, it's localized to a particular area. Right? We want to keep that localized area. If invaders got in, we want to keep them contained. And then, of course, if the bad guys got in, we want to eliminate those invaders. So as we go through this process, think about what's working to contain the damage. What's working? How is that response localized? How do we keep it just in one area? Who's eliminating the invaders? How do we restore tissue function? And then we already know you see, right? Swelling. You see redness. You feel heat. You feel pain. And sometimes you may even have loss of function. So think about these things as we watch the videos and the animations that I have for us. So there are 2 pretty cool videos out there. And I just realized that I didn't change the word blackboard here. So here I thought I did a really good job, and I still have a typo, right? We are in Canvas now, so this stuff is, of course, in Canvas. So we will hop over to Canvas. And we can just go to our pages even, right? Because we have a page for this module of animations, videos, and web pages. So these are the ones you hopefully you already looked at. Here's a really cool one that I highly recommend. He's kind of funny. And so the first one it says we're going to look at is leukocyte rolling. So I'm hoping I can get this going.
At sites of injury, infection, or inflammation, cytokines are released and stimulate endothelial cells that line adjacent blood vessels. The endothelial cells then express surface proteins called selectins. Selectins bind to carbohydrates displayed on the membrane of the leukocytes, causing them to stick to the walls of the blood vessels. This binding interaction is of sufficiently low affinity that the leukocytes can literally roll along the vessel walls in search for points to exit the vessel. There, they adhere tightly and squeeze between endothelial cells without disrupting the vessel walls, then crawl out of the blood vessel into the adjacent connective tissue. Here, leukocyte rolling is observed directly in an anesthetized mouse. The up and down movement of the frame is due to the mouse's breathing. Two blood vessels are shown. The upper one is an artery with blood flowing from right to left. The lower one is a vein with blood flowing from left to right. Leukocytes only adhere to the surface of veins. They do not crawl out of arteries. Some leukocytes are firmly attached and are in the process of crawling through the vessel walls, whereas others have already left the vessel and are seen in the surrounding connective tissue. When the blood flow is stopped temporarily by gently clamping the vessels, we can appreciate how densely both vessels are filled with red blood cells. Red blood cells do not interact with the vessel walls and move so fast under normal flow that we cannot see them. When the blood flow is restored, some of the leukocytes continue rolling, whereas all non-interacting cells are immediately washed away by the shear.
So that's one of my favorite videos. It's pretty cool, huh? And thank you to YouTube, right? They have a website that originally I had taken the video off the website, but nowadays everything's on YouTube, right? What isn't on YouTube? So there's a spot where I want to ask you guys a question.
Vessels are filled with red blood cells.
That might not have been it. Maybe go back a little further. There we go.
Two blood vessels are shown. The upper one is an artery with blood flowing from right to left. The lower one is a vein with blood flowing from left to right. Leukocytes only adhere to the surface of veins. They do not crawl out of arteries. Already left the vessel.
Two pause buttons next to each other. Apparently I can't handle it. All right. So one key point, especially for my anatomy and physiology students, you guys should be able to answer this one, right? So notice she says that the white blood cells, which is another name for a white blood cell, is a leukocyte. And I always suggest to my students that they don't use the term leukocyte because a lot of times they confuse it with lymphocyte, which is a specific group of white blood cells that we're going to talk about later. And so they tend to switch those two terms, and they're not interchangeable. Okay. White blood cell is so much easier to say anyways, right? And spell, too, if you're in anatomies and physiology class, right? If your teacher will accept it, why not write white blood cell instead of leukocyte? But they're saying that they only come out of the veins and not the arteries. So what's some anatomy, physiology reasons on why you could assume that they're not going to go out of an artery?
Because the veins actually are filtering and it's taking the whole blood back to the heart.
Nope. Arteries are thicker. Arteries have muscle layer associated with them, right? Where the veins are much thinner, right? Literally one cell layer thick in some places, especially when you get down to capillaries, right? Capillaries are teeny tiny, just one red blood cell is getting through at a time. So there's another problem though, and it was kind of illustrated when they clamped the blood vessel. Think about the movement, right? So arteries are real thick, so you're not going to get through, but what else as it relates to arteries? The blood flow is what? It's away from the heart, right? Remember, arteries away from the heart, but it's under the greatest amount of pressure. It's moving the fastest, right? So, I mean, and then how are they actually getting out, right? So these endothelial cells are expressing selectants, right? So like little molecules that the white blood cells are able to adhere to. So when I was a kid, one of the islands back home, they had a carousel, right? You know, the horsey thing that goes around, merry-go-round thing, like we have at City Park. But theirs was inside of a building, and there was a brass ring you could try and grab as you went flying by on your horse. I don't know anybody who ever grabbed that ring. But imagine these guys, right? I mean, they're flying down this blood vessel. They need something to grab onto, otherwise they're not going to make it out, right? Out of that blood vessel into the tissue where they need to go. I, on the other hand, never even tried. It scared the crap out of me. But think about these white blood cells, right? They've got to jump ship, right? And you're going to need something to help you jump ship into that tissue. Make sense? Okay. So notice too, and this next video is going to really give us an idea of this localization that happens. So let me shrink this one down. And we're going to look at lymphocyte homing. And again, they say lymphocyte here, and y'all, I think they really meant to say leukocyte, like white blood cell. Lymphocytes are a type of white blood cell, and they usually come later in infection. So I seriously doubt that these are lymphocytes going in. They're actually probably neutrophils, something we're going to talk about in a moment in one of our other videos. So let's go ahead and look at this one.
To visualize lymphocyte homing to a site of injury, a zebrafish larva was anesthetized and its fin pierced with a needle to introduce a small wound. A vein is seen at the bottom of the frame. Because the fin is very thin and transparent, we can watch directly as lymphocytes crawl out of the blood vessel and migrate towards the wound. They are attracted there by chemicals released from damaged cells, invading bacteria, and other lymphocytes. In a zoomed-out view, we can appreciate that lymphocyte invasion is restricted to the wounded area. The static cells that are dispersed in the connective tissue are fibroblasts. In these movies, 60 minutes of real time are compressed into 15 seconds.
So it took an hour. Wrong button, Erica. I stopped myself this time. It took an hour for that to happen, right? What they showed you there. But why were they going just here? What did they say? Why were those white blood cells just going to that one site? The tissue was damaged, right? And the cells were releasing things, saying, I'm injured, I'm hurt. And then microbes, if they got in too, they release substances, right? They're living, they're going to have waste that they get rid of, or just normal stuff that's associated with them that our body has the ability to sense, or in this case, the fish. Okay? And so they're going to head to that area. So another A&P question, anatomy and physiology. What are fibroblast cells?
They build fiber.
Yeah, they build the collagen and such, the fiber that makes up the connective tissue. So they're just there, right? They're doing their job there. And basically they're pointing them out so you don't confuse them with the white blood cells that were running into the area. Okay. So we know, right, we're able to localize it because they're going right to where they're being called, right? Where the damage is happening, they can sense this, they're heading towards that. What do you think those cells are doing when they get there as far as invaders go? They're attacking them, they're eating them. They're doing a process known as phagocytosis, right? So our next animation is going to go into a little bit more detail, but I really like starting out with these because it's real life, right? It's the real thing. I have no idea how they film these videos, but they're super impressive, right? And it's really cool to see the real thing happening, right? Instead of some animated thing, we're seeing it happen for real. So it's in my PowerPoint, but it's also right here. So we're going to go to the inflammatory response. And this one is much more detailed. So it's going to give us a lot of information. Is it just thinking about it, or what's the deal? Push the button again, Erica. There we go. Oh, you know what? I am not going to do this one because it won't go full screen. I'll use the one in my PowerPoint. There we go.
The inflammatory response is an important, nonspecific defense against tissue damage. It begins when injured tissue cells release chemical signals that activate the endothelial cells of nearby capillaries. Within the capillaries, adhesion molecules called selectins are displayed on the activated endothelial cells. These adhesion molecules attract neutrophils, slow them down, and cause the neutrophils to roll along the endothelium. As the neutrophils roll along the endothelium, they encounter chemicals that activate integrins, which are adhesion receptors on their surfaces. These integrins then tightly attach to adhesion receptor molecules on the endothelial cells. This causes the neutrophils to stick to the endothelium and stop rolling. This accumulation of neutrophils along the walls of the capillary is referred to as margination. The inflammatory mediators released by the injured tissue bring about changes in the environment that cause mast cells to degranulate and release histamine. Histamine causes vasodilation and an opening of the junctions between the endothelial cells, allowing fluid and leukocytes to leave the capillary and enter the infected tissue. The neutrophils now undergo dramatic changes in shape and squeeze through the endothelial wall into the interstitial tissue fluid. This process is called extravasation. The neutrophils, followed by other types of phagocytes, are attracted to the damaged site by chemotactic substances released by bacteria and tissue breakdown products. They ingest and destroy invading bacteria.
Pretty cool, huh? All right. And believe it or not, that one doesn't cover all the details, but a lot of it. So we're going to go step by step through one of the diagrams that's in your book. So what caused the release of the inflammatory mediators? So we've got a splinter here, we've got invaders that got in, right? What is causing the inflammatory mediators to be released? What has happened in this picture? We got damaged tissue. What else do we got? What are these little things? We got invaders, right? So we got a 1-2 punch here, right? We've got tissue damage and we've got invading microbes. This is going to send off the alarm, right? Set off the alarm that says, invasion, damage, we need help. So how do the white blood cells get to this area? We just watched this like 3 times, right? Right? They're going to be attracted there, and they're going to attach to the endothelial layer, right, of veins or capillaries, and they're going to head into that area. So it's the increased blood flow that's going to get them there. And then that's why you see and feel what? Pain, heat, redness, swelling. So the redness and the heat are linked. That's the increased blood flow, right? The redness lets you know that there's more blood going there. And guess what? Your blood is hot. It's actually how you get rid of most of the heat that your body produces. How do you tell the difference between an African elephant and an Asian elephant? What do we have at our zoo here? Anyone know? We have Asian elephants. They have little ears, right? African elephants, huge ears. Why? The climate they live in is what? Hot. They literally pump their blood through their big ears and fan them to cool themselves. How do we cool ourselves? Where does our blood go to cool us? It goes to your skin. That's why you get red when you start working out, right? Your blood flow increases to your skin, not because your skin needs more blood under those conditions. Your muscles do, right? But you got to get rid of the heat that the muscles are producing. And the way you do that is at your skin surface, right? Then you start sweating and you get convection, right? And it helps cool you down. So that's why when we have the increased blood flow, it gets hot, right? Because blood is hot. Now, the swelling is because those blood vessels, as we saw, become leaky, right? And so fluid from the blood itself starts leaking into that area. So that's the swelling. Well, that swelling then pushes up against your pain receptors in that area, and that's why it's painful. So in that fluid, what important proteins enter into our tissue? Who found the answer to that one? What important proteins in our blood is going to help us out in this situation? Albumin is a protein, but transferrin, another protein, trans, meaning transport. Ferrin refers to a particular element. What element? Iron, right? And iron is very necessary for bacterial metabolism, but we also need it in our bodies. And we don't want the microbes to get it. So transferrin is going to bind to our iron and keep them from binding to it. And it also helps us transport our iron, because iron is not soluble in water, and our blood is mostly water, right? The aqueous phase is mostly water. So that's why that's in our blood, and that's why that can be helpful in helping us retain our iron. Complement is a series of proteins that we're going to learn about that can help activate even more inflammation and can actually cause cellular destruction as well. So we're going to spend a significant amount of time a little bit later on this whole system of proteins that are found in your blood that are going to get into the tissue when you have this leakage that happens. Antibodies, right? Your antibodies circulate through your blood. They too are proteins, and they do have protective ability. They can bind to specific invading organisms and help in the destruction of them. And we're going to spend a lot of time talking about antibodies a little bit later. And then clotting factors. They're going to help wall off the area. So just like when a blood vessel gets damaged, right, it's going to help wall off that blood vessel so we don't have uncontrolled leakage of blood into the tissue. Right? We want what goes in, we want that to be controlled, right? So these clotting factors, which will help close up a damaged vessel, will also help encase the area. So almost like putting crime scene tape up around the area, right? This hopefully will keep stuff in and keep other stuff out. So how do they get out of the blood vessels? What's happening here? Right? They're going to be attracted by those adhesion molecules. They're literally going to adhere, and then they're going to squeeze through into the tissue. So what's going to start that whole process, though, right, is those what we call pro-inflammatory cytokines. These are molecules that are chemical messages of the immune system. Right? Cytokines are the particular chemical messaging that's happening. For the immune, that's for the immune system. For the endocrine system, what's the signaling molecules referred to as in your endocrine system? So remember, the hypothalamus talks to the anterior pituitary, who bosses everyone else around. What do we call those things? Hormones, right? Those are chemical message signals. That's just the endocrine system. In the immune system, oh my gosh, you think endocrine is a nightmare? Just wait and see. We just don't even know all of the cytokines and all the interactions. We know quite a bit, and man, that's a monster of a book all on its own. So the good news for you guys is we're just going to scratch the surface as it relates to the communication that happens in the immune system. But cytokines are major players, right? They allow the different cells to talk to each other, right? And get this job done. So those pro-inflammatory cytokines, of course, are going to cause the changes that we saw in the endothelial cells, get those adhesion molecules produced, because otherwise the white blood cells are just going to keep flying by, right? They're not going to have anything to grab onto. So once those adhesion molecules are there, the white blood cells are going to grab onto them. And then diapedesis is that process of them actually squeezing. Diapedesis actually means oozing, right? So that's them squeezing between the endothelial cells of the blood vessel to get into the tissue where the damage is. So, what did we say these were? In that last animation we watched, who were the first white blood cells that got called to the scene? Neutrophils. These are phagocytes. These are eaters, right? By phagocytosis, they're going to eat up the invaders. These guys are only in your tissues during inflammation. And they're going to be the first to arrive. But under normal circumstances, they're not found in your tissue. They're just circulating in your blood. Next would come, anyone know? These guys are sometimes referred to as the big eaters. Monocytes, and when they're in your tissues, they differentiate into what we call macrophages, right? So macrophages, which, as we said, are derived from what is called a monocyte in your blood, and macro, as that part of the name implies, these guys are really good at eating. They're big eaters. They can eat a lot of stuff. And then last on the scene, if necessary, are going to be a group of cells known as, they end in cyte. These are your lymphocytes. And we're going to talk about those guys when we get to our adaptive immune response. Her question was macrophages, they the complement system? No. The complement system is a series of proteins found in your blood that will leak into your tissues during inflammation. These are actual cells. And they have different jobs, but as you see, right, the main thing we want happening right there in the beginning is we want cells eating those invaders, right? We want phagocytic cells, cells that are going to eat by phagocytosis the invaders. So what do? What did we say? What are they doing in this picture? They're eating the bacteria, right? They're eating them up by phagocytosis. So they're going to destroy and remove the invaders. And you see both neutrophils here and macrophages. We do have some cell death that happens, right, when you have damage, and you may even have debris. So they're going to remove that as well, not just the invaders. They're going to clean up the scene. So sometimes when you have damage and you have inflammation, you also get pus. What's in pus? Yeah, a bunch of dead neutrophils, right? A bunch of dead neutrophils. That's not good news, right? If our cells are dead, right? That's not good. If you have pus, is that good, y'all? No. It means that your body is not able to take care of the invasion, right? Your neutrophils are dying, and we're not taking care of the problem. So, in addition, of course, you'll have some tissue debris there. And then the really bad news, which is why you don't want to come in contact with anyone else's pus, is what else is still there? The invader, right? The pathogen, whether it be usually it's bacterial, right? When you have pus, but it could be viral as well. And this is a pretty good sign that inflammation is failing, right? When your neutrophils are dying and they're not killing the bad guys, that's not a good sign. That's serious infection. You need help. Right? And the pathogens are there, and this is why, right, you don't want to be exposed to somebody's pus. There's a reason why people go, ooh, other than it looks gross, right? So, again, in the beginning, right, we're going to start with injury of cells. That's going to release that signal, those cytokines that say, hey, we're in trouble. Especially if invading microbes get in, cells can detect that. They're going to scream out for help, right? And so that process has begun. Mast cells might even degranulate, as they saw in the animation, and release histamine. This is one of those, again, pro-inflammatory molecules, right, where it's going to cause the endothelial cells just to express those adhesion molecules, and the cells are going to start heading into the area. But notice that the macrophage was already there, right? Resident macrophage. You have resident macrophages all throughout your body. They're always in your tissues. So they're part of your first line of defense when bad guys get in. But again, usually a lot of them get in. You don't have enough there to take care of the problem. So you've got to call in reinforcements. That's what basically inflammation is, right? We're calling in reinforcements. We're going to get neutrophils, which are other eaters, and even more, right? Notice it's a monocyte here, but it's going to turn into a macrophage in the tissue, right? So notice this one, it says it was recruited. It wasn't on scene, right? He was called up. And so, again, them attaching to the endothelial walls and then squeezing through and getting into the tissue layer. So let's review. What was the purpose? One of them is to contain the site of damage. How do we contain it? What was one of those important things that helped contain? It was one of the proteins. And that's going to help with iron. Antibodies, maybe. The clotting factors, right? The crime scene tape. We're going to wall off the site. How do we keep it local? Why is it the white blood cells were going to that site? Yeah, the tissue, the cells there, the invading microbes, right? Those are all giving off signals that are calling the white blood cells just to that area, right? When that signal is released, it's to that area and that area only. Right? They're following the signal. That's how we can keep it a localized response. How do we eliminate the invader? Yeah, the one thing that we've learned so far is the phagocytic cells. That's only one of the things that happens, though. But it's a major component, right? Those neutrophils and macrophages gobbling up and eating them by phagocytosis. And then again, we've had damage, so we've got to restore that tissue. We've got to clean up the mess. If we're able to eliminate the invader, that is. When you've got pus, we're not reaching elimination. So what do we see? How do we know inflammation is happening? Right? So we see that swelling. We see the redness, the heat. We experience the pain. And sometimes we have loss of function. Remember, why is it hot and red? Is the increased blood flow to that area. Why is it swelling and why is it painful? The fluid leaking out of that blood. Right? The fluid swells it up and pushes up against the pain receptors. So we say ouch. And then you may have loss of function depending on where that happens. So this sounds like an awesome story, right? Takes care of every problem. Not really. We already said if you got pus, it ain't taking care of the problem, right? Your neutrophils are dying. So there's different types of inflammation. Acute inflammation, that's short term, right? The macrophages are able to clean up damage by digesting dead cells and debris, right? We take care of the bad guy, we clean up the mess, all is good in Denmark. When acute fails, you have what we call chronic inflammation. And you can have situations where macrophages accumulate. They actually fuse together to form what we call giant cells, or you may even have granuloma formation. So what disease of the lungs do giant cells and granuloma formation, do you see this? There's one where you really tend to see this more than any other disease. It's abbreviated TB, tuberculosis. So what is a giant cell? It's a whole bunch of macrophages fused together. So it's not just one, but several. And why do they do this? Because the invader's not destroyed. Right? So the invader the macrophage engulfed it, right? And it can't kill it. So more macrophages actually swallow that macrophage. And then if that continues, you may even call in another set of cells that's usually involved in this group of cells that ends up forming. So who comes on scene next? And you get the formation of a granuloma. It's a type of lymphocyte. Lymphocyte. Nope. T cells. T cells. So I stole a cool picture from the internet. I give credit when I steal, by the way. I borrowed this from this journal. on the website. I always have it in my notes, by the way, if you want to know where it came from. So this shows you two different types of granuloma formations that happen with tuberculosis infection, right? TB. So this top half, right, the whole circle would look like this top half, right? You would just mirror the image on both sides. And you'll notice from their ledger and the descriptions on the sides here, you've got macrophages where the bacteria are actually busting out of them. They're what are called necrotic, right? The M/O is an abbreviation used for macrophages, right? So this is a macrophage, this is a macrophage, and this is a type of macrophage. And so these macrophages are associated in gobbling up the bacteria that are busting out. But they're signaling in such a way that notice that we even have some neutrophils coming in here eating. Here's a neutrophil. But notice on the edge of this you have other cells. You have a B cell, and you have the T cells. And in this case, it's a type 1 T cell. So in this type of environment, there's bacterial killing that's happening, potentially. It's more of an aggressive state. Here, unfortunately, at the bottom, notice we've got these giant cells. You see there? So these are macrophages that are fused together. We also have this other type of cell known as foam cells. We have a lot of other macrophages out here, right? Type 2. And macrophages can switch between type 1 and type 2. But the problem here is that you've got regulatory B cells and you've got regulatory T cells. So this, you're not having the bacteria busting out of these giant cells. Instead, it's contained. And you think, oh, well, that's good, right? No. Because the bacteria are inside of our cells and they're not busting out for the most part. So they're contained. They're almost hidden. And the other supportive cells are like, okay, we're okay with this. We're just going to keep it all in this one area. So this granuloma grows and grows and grows. And gets larger and larger and larger. And the problem with that is that it starts obstructing lung tissue. Right? You need gas exchange to happen. If you have this big old ball, right, of TB-infected giant cells in this granuloma, then you have less gas exchange happening in that area. Now, this is a slow-growing bacteria, so this happens over a long period of time. Another name that was commonly given to this infection was consumption, because eventually, over time, it consumed you. Right? In the movies, they believe Doc Holliday probably died of tuberculosis. Right? Other famous people. If you actually drive down next to Charity School of Nursing for Delgado, down on, is that Claiborne? You'll pass a building that says Tuberculosis Hospital. An old building that still has that written on it. It was a significant problem before we had antibiotic treatment, right? They just put people in hospitals, infirmaries, and basically when they were in the end stage and just waited for them to suffocate to death and die. It wasn't anything they could do for them. The good news, when it's in this state, when the bacteria are actually getting out of the macrophages, is that antibiotic drug treatment can get to these bacteria, right? Because they're not inside of our macrophages. There's a period when they're outside of those cells. So referring to favoring bactericidal events, right, where we could kill bacteria. But Also, because they can hide inside of our macrophages, this is why treatment for tuberculosis can be very long-lived. You're talking about 6 months or longer of antibiotics. This is the bad news with that, is most people don't keep up with that long of a treatment, right? And then you have resistance that builds up. So we have multi-drug resistant strains of tuberculosis now, and extremely drug-resistant strains of tuberculosis. So there was a gentleman by the last name of Speaker several years ago that apparently had tuberculosis and decided to get on an airplane and fly to another country for a wedding. Claims his doctor didn't tell him he couldn't go. Think that was true? No. So there's a huge panic because, everyone on that plane was exposed to him. And it's respiratorily transmitted. And guess about how many bacteria you have to inhale from that person to get the disease? As little as 10. 10, y'all. I don't know about you, but I've been seriously pissed at that man for getting on that plane. I followed the story for a while, and as far as I could see, nobody thankfully got it from him on that trip. But it was a huge deal. And the fear was that he had extremely drug resistant, but no, he had multi-drug resistant tuberculosis. So again, he had a pretty serious form of the disease, of the bacteria. Not something to laugh about. So, inflammation. It can be damaging, right? So it's sometimes referred to as the sprinkler system. So how is a sprinkler system similar to the inflammatory response? Right, we prevent from spreading, right? So when the sprinkler system goes off, it stops the fire from spreading. But especially if it happened in a computer lab, what just happened to our computer lab? It's destroyed permanently, is it not? Right? Electronics and water, not best friends. Right? But the building didn't burn down, yay. Right? And so sometimes we kind of make the same sacrifice in our bodies, that we will destroy even our own cells, right? Our own tissue, trying to get at the bad guys. The good news is sometimes we can afford to lose, a part. But when this happens in delicate systems, this can be a real problem. So just like a sprinkler system, right, it's going to prevent the spread. But it causes damage. Enzymes, toxic compounds from phagocytic cells are released, and they'll actually damage our own tissue sometimes. So although those animations, right, and the videos we watch, they look so pretty and clean, oh no, it is not at all like that. It is full out serious war. No big deal if it's a cut on your finger, right? Like I said, we can handle a little bit of damage there. Small amount of damage, small area. We can take care of that. Who cares if you end up with a scar on your finger? It's better than still living, right? Better than losing a finger or a hand. If this happens in some delicate areas, like the membranes surrounding our brain and spinal cord, then it can be quite severe to have inflammation there and even life-threatening. And part of the problem as it relates to the brain and spinal cord is that influx of cells and fluid. What is your spinal cord and your brain encased in for protection? It's pretty hard. Protects it pretty good. Your skull. It's bone, right? Does bone flex like skin does? Yeah, when you have inflammation, when you have buildup, you're crushing your brain and spinal cord. Right? That pressure goes inward because it can't go outward. Bone is not flexible. Right? That's why sometimes they'll literally drill a hole in your skull to relieve the pressure. Right? Your skin, on the other hand, can stretch. Right? So inflammation at the skin level We've got room for that. So cell death as it relates to inflammation. What's apoptosis? Cell death, and do we have inflammation with it? No. This is cell death, programmed cell death, cell suicide in some cases, that does not trigger inflammation. And that's important. Because why would you not want to trigger inflammation every time a cell died? Think about your cells and how often they die. Do you want inflammation happening every time one of those babies dies? No, you'd be in a constant state of inflammation all over your body, right? Red blood cells only make it about 120 days. They're long-distance truckers, y'all. They're on the super highway of your blood. That's a pretty tough highway, too. One red blood cell at resting heart rate, y'all, can travel the length of your body in a minute. At resting heart rate. These are serious long-distance truckers. They've got a rough road. Anyone know what organ in your body is responsible for clearing those guys out when they get damaged and destroyed, your red blood cells? Your spleen. Your spleen. If you don't have your spleen, that's the one organ you can live without if you had to. They won't do a transplant for you if you lose it. Is your liver. Your liver will take over a lot of the functions that your spleen once did. So, yeah, we wouldn't want to be in a constant state of inflammation all the time. That would really not be good. It would be difficult to support that kind of response all the time, right? Especially since it's not necessary. But is there sometimes when your cells die that it's not because it was the end of their lifespan? Think about tuberculosis, right? Some of those macrophages that are dying. They're dying because of what? They're invaded by a microbe, right? So cryopatesis is where we recognize, right? There are pattern recognition receptors that are triggered. We recognize that this cell, there's something wrong other than its life is over naturally. So this is where the cell may undergo cell death with an inflammatory response, where there's something not quite right in Denmark, right? There are receptors that are being triggered that say, hey, there's a problem here. We need backup. Call in reinforcements. So how does the system know, right, that the cell died from invasion by a pathogen? As I said, we have receptors that let us know, right, that foreign substances are there. And therefore we need backup. We need inflammation. So the next thing we're going to look at is phagocytosis. And our two main phagocytic cells are our macrophages and our neutrophils. We want to compare and contrast the similarities and differences for them. And these two videos are really short, but super cool. Someone close the door for me, because I still have 10 minutes, and I'm going to use them. All right, so we're going to look at the neutrophil chase first.
Neutrophils are white blood cells that hunt and kill bacteria. In this spread, a neutrophil is seen in the midst of red blood cells. Staphylococcus aureus bacteria have been added. The small clump of bacteria release a chemoattractant that is sensed by the neutrophil. The neutrophil becomes polarized and starts chasing the bacteria. The bacteria, bounced around by thermal energy, move in a random path, seeming to avoid their predator. Eventually, The neutrophil catches up with the bacteria and engulfs them by phagocytosis.
So this one even has cool music. Right? But that's the real thing, y'all. The real thing. So then the next one, again, really shows how specific this response is.
Taken from the blood of the graduate student, are mobile cells that will quickly migrate to sites of injury to help fight infection. They are attracted there by chemical signals that are released by other cells of the immune system or by invading microbes. In this experiment, tiny amounts of chemoattractant are released from a micropipette. When neutrophils sense these compounds, they polarize and move towards the source. When the source of the chemoattractant is moved, the neutrophil immediately sends out a new protrusion, and its cell body reorients towards the new location.
So it almost reminds you of a protozoa that can move like this. What does that look like to you guys? Amoeba, right? Just like amoeba move, right? That's how they're moving, right? They're pushing their cytoplasm. They're chasing down that attractant, going to that area where they're being called. So for phagocytosis, right, the major steps is getting to that area, right? Chemotaxis means chemicals. Taxis referring to that movement. So those chemicals are calling it to that area. Then they're going to recognize the foreign substance. And there are things that will help them do that and attach to it. So they got to get there first, then they've got to recognize and attach, then they're going to engulf. When they engulf it, they're going to put it into a vesicle we call a phagosome. That phagosome is then going to fuse with a lysosome. So guess what we do with the name? We fuse it. So it becomes a phagolysosome. In that phagolysosome, because lysosomes contain digestive enzymes, we're going to destroy and digest the invader. And then we're going to spit out the trash by exocytosis. So those are your 6 major steps of phagocytosis.
In phagocytosis, phagocytes are attracted to the area of invasion by chemical products of the microorganism, phospholipids released by injured mammalian cells, or by components of the complement system. The phagocyte moves into the area of invasion and then attaches to the microorganism. The attachment is mediated by a variety of surface receptors, including antibody, lipopolysaccharide, and complement receptors. For example, the C3b component of complement coats bacteria or other particles and then binds to C3b receptors on the phagocyte. This process of coating to enhance phagocytosis is called opsonization. The microorganism is then engulfed by the phagocyte into a vacuole known as a phagosome. Vesicles in the cytoplasm called lysosomes fuse with the phagosome, releasing digestive enzymes such as lysozyme and proteases into the phagosome. The structure resulting from this fusion is called a phagolysosome. Inside the phagolysosome, microorganisms are killed and digested. Finally, the digested contents of the phagolysosome are eliminated from the phagocyte by exocytosis.
Right? So I know I've probably lost your attention to a certain extent. So we're gonna review these steps, which would be a good thing to do anyways, at the beginning of the next lecture. And then, as I said, sometime on Friday, I'll have our next lecture posted for you guys. Those of you guys that want to even maybe read ahead, I'm going to go into all the different types of white blood cells next. That's the next section we're going to go into, which leads in good to talking about the specialization, right? So you'll notice I even have them at the end of this one. And I'll post this one too, right now.